You have a quiz for today where in the quiz you step through figuring out how big are the reactions on each end of a beam. And next time I'm going to go through that process really step by step, one small step at a time. Today I want to do something a little bit different and maybe go a little bit faster just to let this whole process wash over you. And I'm going to use scribbly sketches that I made on a piece of paper, nothing fancy. So we'll think about what would this be like if we were just sitting at our desk scribbling stuff. So we've talked about drawing a free body diagram, and if we wanted to figure out the reactions on this trailer here, we would do that. Here's a picture of the trailer, and now for a free body diagram, we'd want to isolate that trailer beam and draw it, and we'd want to put forces and reactions on that beam. So here's my free body diagram of that thing. Here's another one. Here's my scribbly one. This one happens to be metric, so it's 3 meters long, and it has a load of 3,000 newtons, or 3 kilonewtons, sitting not in the center, but off to one side. And what if we wanted to figure out how much weight is on each end of this thing? First of all, what kind of support reactions are there at each end of the beam? So notice we've got a round thing under here at B and a thing that looks kind of bolted here at A. What are those? A is pinned and B is a roller. So this beam would be free to expand and contract as the weather changes. Okay, here's my picture of my beam, and here's where I scribbled out a free body diagram. And because A is pinned, I made an X reaction and a Y reaction. And because B is a roller, I made just a Y reaction. Okay, so here's where I'm solving it. I rummaged around in my toolbox where I have my equilibrium equations, and I found my moment equilibrium equation. Sum of all moments equals 0. I'm going to take moments around point A, and all of those moments have to add up to 0. And what are they? Well, I've got a clockwise moment caused by this 3 kilonewton force. It's clockwise, so it's a negative moment. 3 kilonewtons times 1 meter, that's the distance, so force times distance, and it's a negative moment. Then up here at the far end, I've got force times distance. I don't know how big that holding up force is, that reaction at B, so I'll just write B, and I know that it's 3 meters from the end. So there's my equation, my equilibrium equation. And now I can add 3 kilonewton meters to each side to get rid of that negative side. And now I have 3 kilonewton meters equals 3B kilonewton meters. Or in other words, B must equal 1. So B is 1 kilonewton. Now I'd like to find out how big is the reaction at A. And I'm going to use the sum of all forces in the y direction equals 0. And what have I got? I've got A pushing up, so it's positive. I've got 3 pushing down, so it's negative. And I've got 1 pushing up, so it's positive. So here's my equilibrium equation. Sum of all forces in the y direction equals 0 equals plus A minus 3 plus 1. And smushing those numbers together, I find out that A equals 2. So now I can write 2 kilonewtons under the thing at A. And, oh yeah, I wanted to say something first before I just flash that on the screen. Look at this free body diagram. And remember what you know about equilibrium, that the sum of all forces in any direction have to add up to 0. And think about what you've got happening in the x direction. You have an x reaction here at A, because that's a pinned connection. What other x stuff do you have? You don't have any. So, if all the forces in the x direction add up to 0, and you've only got one x force, it must be 0. So we can just ignore that x component. All right, here's another one. This one is not metric. This is imperial units. And we have a beam with a weight sitting on some angle clips. And let's find the reactions at A and B. So here's my sketch. Now, why did I draw a 1,000-pound arrow in the middle? I did that because we're told this beam weighs 1,000 pounds. And I could replace that whole long beam with just one arrow here in the middle. So the weight of the beam is acting in the middle of the beam. That's why I made that arrow there. And then here's the 6,000-pound weight over 3 feet from the end. And these appear to be pinned connections, so I've got x and y reactions at each end. We don't have enough information to be able to solve the x and y reactions. We know that they're equal and opposite, but that's about all we know. So we're going to ignore the x reactions, and we'll just think about the y stuff. And that's what we are interested in anyway, how much weight is coming down on each end. So I get my equilibrium equation, sum of all moments equals 0, and what have we got? We've got 6,000 pounds times a distance of 3 feet, and it's turning in a clockwise direction, so that's a negative moment. Then we've got the weight of the beam, 1,000 pounds, 6 feet from the end, because it's in the middle, and it's also turning clockwise, so it's also a negative moment. And then we've got B pushing up on the end, and it's turning counterclockwise, so that's a positive moment. And its distance is 12, because B is 12 feet from A. So there's my equation. Now, smooshing the numbers together, I wind up with 18,000 and 6,000. And I'm going to add both of those to the other side so I can get rid of the negative numbers. So I've got 18,000 plus 6,000 equals 12B. I'll smush them together a little more. 24,000 equals 12B. So what could you do? You could divide both sides by 12 and find out that B must be 2,000 pounds. So I'm going to write 2,000 pounds under B. Now I'll use my other equilibrium equation. Sum of all forces in the y direction equals 0. And what have we got? A going up, so it's positive. 6,000 coming down, 1,000 coming down, so those are negative. 2,000 going up, so there's all the numbers. And they all add up to A equals 5,000 pounds. So I can write that under this end of the beam. Here's another one. This one is weird. It's got a force pulling sideways instead of some weight pressing down on it. This thing is actually a truss, and the reason I say that is it's a thing made out of triangles. So there you go, that's a truss. This is a truss with a force pulling on it, and look here, we've got, what have we got? What is that? It's a pinned connection, and here is a roller or a rocker connection. Okay, and we're going to draw a free body diagram of this thing. When we draw a free body diagram of this thing, we don't need to worry about these bars in the middle. This is basically a beam shaped like a trapezoid. So that's what I drew there. I've got my 12,000 pound force. I've got, now I'm not sure which direction these reaction arrows go. I'm just kind of guessing. it kind of looks to me like if we're pulling on the side here, probably this truss is going to be trying to push down on that rocker. So I'm picturing that there'll be a reaction pushing back up. And that means on the other end, there has to be an equal and opposite reaction going the other direction, in the y direction. Then for the x reaction, if we've got 12,000 pounds pulling to the right, this x reaction must be pulling to the left. So, okay, there's that. Now, we're going to use our moment equation to figure out the reaction at B. And remember that moment equals force times distance. What are we going to do about distance? Well, what we are going to do is, first we'll think about, okay, the distance is from the pivot point perpendicular to the line of action. And how far is it from the pivot point perpendicular to the line of action, going straight up? How do we figure that out? Okay, I figured 4 1/3 feet. That's great. How did I do that? Well, these triangles each triangle has a side that's 5 feet long. So notice that all of these sides are equal. And what that tells us is that we've got an equilateral triangle, or a bunch of equilateral triangles, because each side is the same length. And what that means is that each angle is the same length. And you might remember from math class that in an equilateral triangle, all of those angles are 60 degrees. So I made a triangle here, and I split it in half. There's a 60-degree angle. There's a 5-foot hypotenuse. And from that, I could figure out 4 1/3 feet. Or I could do what I like to do, is just go draw it in CAD and see if I really do come up with 4 1/3. Okay, so now I'm going to go 12,000 times 4 1/3, and I'll make that a negative moment because it's trying to turn clockwise, plus b times 10. And smushing the numbers together, I get this, 51,960 equals 10b. Dividing both sides by 10, I find out b is 5196 pounds, so I can write that. And now, if all the forces in the x direction add up to 0, and one x force is going 12,000 in the positive direction, this x reaction in the negative direction must also be 12,000 pounds, so I'll write that there. And finally, all the forces in the y direction add up to 0. What have I got? I've got A coming down and 5196 going up, so A must be 5196 also. Here's an example out of our book, similar to that one we looked at earlier. So he's got a structural steel beam sitting on a couple of clips, and here's his example of how he drew the free body diagram. Well, that is very similar to the first problem in your quiz. It looks like this. And in the quiz, I'm just going to step you through how you would figure these out. Now, the numbers are kind of weird, I suppose. First of all, this is metric. So we have 40 kilonewtons at one place, 50 kilonewtons at another place, and we're going to figure out how much weight is on each end. And I did give you the answer that you should come up with here, just so you can check your work. But you'll find it in the quiz. And then here is a truss. The other thing the example we looked at was a truss. This is a truss, but it's a different shape. And here are the answers that you should come up with after you figure out the sum of all moments. You'll find that B is holding up 5,000 pounds, and then A is holding up 4,000 pounds. But we went kind of fast here. I just kind of blew through this. I wanted to let this wash over you. And in the next lecture, we'll go through more step by step and carefully.